Okay, so we are in kind of discussion for the double differentiation. Single differentiation itself is very high when we see the multivariate case, multivariable case, and then we are talking about double differentiation. So, but I think it's not should not be very complex in a way that we are only calculating the differentiation of function along axes means uh, partial derivative along x-axis and partial derivative along y-axis. So double differentiation along x-axis and double differentiation along y-axis. So if I have two independent variables x and y, then function over x and y is fxy. If that is z, then z equal to fxy. Then dz by dx is the partial derivation of z along x-axis and dz by dy is partial derivation of fxyz along y-axis. What is a kind of uh, double differentiation? Okay, so d to z by dx square, d to z by dx square, and d to z by dy square. So these are the kind of double differentiation. If I say d to z by dx square, if I say dz by dx, then it is fxx fxxy dz by dy, then it is fyxy. So we also calculate fxxxy, that is double differentiation, fyyxy double differentiation, fxyxy double differentiation, fyxxy, that is double differentiation, where fxyxy is dy dy of fxxy, fyxxy is dy dx of fyxy. So these are cross differentiation, and fxy fxy equal to fyxxy. So these are the things that we have seen. Now I have a kind of, this is x-axis and this is y-axis. So I have a kind of a thread, but it is a rubber band, and if I pull it and leave it, it goes sinusoidal like this. So at the center, so now consider that this is x-axis. Okay, if this is x-axis, and okay, so what is the variation? We have talked there are two kind of variation. If I move along x-axis, then function over x-axis is changing. So consider this height being kind of y-axis. So this is x-axis and this is y-axis. So, or the way we did the convention. So there is nothing that way. So this is x-axis, this is y-axis, this is z-axis. So consider that I am pulling the thread like this. So there is a variation in the vertical area. Here there is no variation. Okay, so here nail is there, here nail is there, here there is no variation. But we move along toward the center, then variation is maximum. Means the height is maximum. Then if we go along, then height is minimum, and here it is zero. Now, so there is, if I move along x-axis, then height varies. Okay, so this is one independent variable is x-axis. But if any place, so here x is constant. Here any point x is constant. So here x is constant, but if I leave, then it will go like this. So based upon the time, also height varies. So height varies because x is growing, but at any x, if I see and make the x fixed, so when I grow in x, then I keep time fixed, and when I fix the x, then with the variation of time, the height varies. So if time is fixed with the variation of x, height changes. Here height 0 and height grows and height comes to 0, which x constant at any point in x with variation of time height change. So the height is variable, is dependent upon x and t. So height equal to fxt. Okay, now I have to calculate fxx xt, ftt xt, fxt xt, and ftx xt. Okay, so what is fx first? So fx xt. Fx xt means if time is constant, then with 1 unit variation in x direction, how many unit of variation in vertical direction we are seeing. So if string is like this and I am moving here, then there are 2 points I'll take. Suppose there is a delta x distance between these 2 points. So first point, second point, first point, second point. First point at any moment, what is the height? Second point at the same moment, what is the height? So that difference is delta z. What is the difference in x? That is delta x. Delta z by delta x. If delta x tends to 0, means per unit change, then dz by dx, dfxt by dx. That is partial derivative along x-axis, along first component, that is x-axis. There is no y-axis or something. So another is time. So one axis is x. So multi-dimensional never means that it is x, y, z and like that. It can be any other thing also. So fxxt is partial derivative along component x rather than axis x. So along component as fxxt, if we want to calculate, that is delta z by delta x, that is dz by dx if x tends to limit x tends to 0. Okay, so suppose that fxxt is sine x sine pi t, means both are sinusoidal. If I move along, if my time is constant and if I move along x-axis, it will make a something curve like this. So it is sinusoidal movement of the vertical distance. If we move x, so we can say sine x. Whereas if x is constant, then the way it moves, okay, at any particular is, that is also sinusoidal. We can make sine pi t. So, as per the first component x is concerned, the vertical changes as per the sinusoidal. Second component t is concerned, the vertical changes as per the sinusoidal. So, there can be variation. There can be a constant also. So, some constant sine xt instead of sine x, it can be some kx, and sine pi t, it can be some sine k2 pi t. So I'm just for simplicity sine x and sine pi t I'm making. So dfxt by dx would be cos x sine x variation, differentiation is cos x sine pi t, keeping time as constant. So fx xt is cos x, so that is positive. If there is a positive displacement up to pi by 2, up to pi by 2 means up to half. If I keep the time constant and move like this, then up to half, if there is a positive displacement along x-axis, then there is a positive variation in z-axis because it is growing. We can see, right? Yes, it is growing. The height is growing. If height is growing, means if I grow x in positive direction, height is also growing in positive direction. So dx by dz by dx is positive. D2x by dt, d2z by dx square, double differentiation. So cos, if I differentiate, it will become sin x minus sin x. So this proves that even though the change in z per unit change in x is positive, but change in dz by dx, change in rate of change of z per unit change in x is negative. Can we see this? So if I move along at any time constant, so there is partial derivative. If I move from here to the center, then for any positive change in x, there is a positive change in z. That way it's positive. But the rate of change in z is negative when I move from here to center. This proves that the whatever the change, okay, the rate of change means per unit change in x brings how many unit change in z. So rate of change as we move from here to here is decreasing. If that is the case, then at the center, just left side of the center, the change in z. Okay, if I compare change from here to here, here to here, here to here, the change in Z is decreasing. Here, the change in Z, the change what we are seeing in Z is more. As we go, it becomes a smooth. So this is not, this is convex. This is convex if single differentiation is concerned. But if you go for double differentiation, then it is concave. Because whatever the change in Z we are seeing, like if I have a ball and if I drop the ball, okay, then change in Z, what we are seeing as it goes down is higher. That's why there is acceleration. But if comes down to up, then change in displacement per unit time we are seeing less. When it reaches here, then it is change in displacement is zero. So acceleration, if it is going down, is positive, where it is decelerating when it is coming up, something like that. So change in x, change in vertical side, change in x is positive because we see z growing. But change in vertical side, d of dx, d by dx of dz by dx is negative. So here change in z is more, where as we go smooth, it will become smooth. So change in z is less. So this is fxx xt. What about ftt xt? If that is we want, then at any x, earlier we had at any t. Now at any x, anywhere we take x, here x. Now if I vibrate this, then it is going up and down. So at that position, with if we take independent variable as time, so with function of time, vertical is moving up and down. So ft xt is nothing but velocity. Okay, how much z is varying here with the variation of time is velocity at that moment. Okay, now ftt xt is acceleration. So again it is sinusoidal. We said that fxt is sine x sine pi t. So sine pi t means if I differentiate first time it is cos pi t. Okay, pi cos pi t. But if I differentiate again, it will become negative. This proves that okay, so at any x, the speed is growing. If I grow the time, okay, if I just leave this, then if we grow the time, so if time is zero here and it is going up, the time is growing, then the speed is growing. But acceleration, this is the way we said, like right. If I drop this, while coming up, there is a deceleration. So when a string when a string came here, went down, came here, when it is coming up, so at initial phase, the velocity is high. When it is going up, 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 and it reaches a maximum level, then velocity is zero. So sine pi t, first differentiation ftxt is positive, where fttxt is negative. So dual differentiation means acceleration. Change in velocity is negative, means beginning when string is at this level and it is going up at the beginning, velocity is high. So string is like this. Now I moved like this. When I release this, it came to middle, went down, came to middle, and went coming up. So when it is at middle, the velocity is very high. Slowly velocity is decreasing when it is coming up. So this is the story of FTTXT. What about FX? What about FXTXT? So first differentiation, partial derivation with respect to x and then t. So first we have to keep t constant, then we have to calculate fx. So we have already calculated fx. So d effect d of d by dx of fxt, d fx xt. So that is positive. So we have to calculate. So that comes as cos in variation of function of cos. So cos x sine pi t. Okay, now we are calculating f xt xt. So fx anyway we have calculated. Now we have to keep x constant. Whatever we have got through fx xt, fx xt. Now t x we have first t was constant. Now x we have to keep constant. If x is constant, okay. So if x is constant, then what variation we are seeing in t, what variation we are seeing vertical side if there is a unit change of time, that is fx t xt. First we calculated fx, now we are calculating ft based upon, but ft on fx what we have already calculated. So it will be cos x and pi sine cos pi t. If the initial function is sine x sine pi t, then it will become cos x sine pi t first time, next time cos x pi cos pi t. So it is positive. Okay, so sine fxt xt. First, we have to do partial derivative along x-axis, keeping time constant, and then keeping x constant. We have to do partial derivative of whatever derivative we have achieved along t component. So first is rate of change in z when there is a unit variation of x. If that rate of change what we have got at particular x, x is constant next time. At particular x, that rate of change in z that was seen against unit change in x, how much that is changing per unit change in the time. Okay, so we saw that rate of change in x, if there is a positive direction x is changing, z is also changing positively, because see z is high, here z is less, at center z is high. So when x is growing, z is also growing. One case. Next is at particular x. If I know that z is growing, per x is growing, at particular time, if time is growing, then z would grow or not? Z would grow. If it is positive, then at particular time z is growing. Okay, d2z by dt square is negative. dz by dt is positive. So if I do like this, then at any moment, at any x, it is the string is going up with variation in time. Okay, at any time, if I grow in x, then string is again going up. At any moment, if x is growing, string is growing in height. Now, at any x, if time is growing, string is again growing. So, fxt xt is positive. What about ftx xt? So, at any moment, at any position of x, at any position of x, fxt, first function, that is sine x sine pi t, would grow with unit change in time or not. So it would grow. So that we have already calculated ftxt. So we are calculating now ftxxt. So first, with constant x, if variation in time brings positive variation in vertical side, it brings positive variation. So if I do like this, at any moment of x, with growing time, the vertical direction is growing. If I know dfxt by dt, that it is growing, now I have to keep time constant at any moment. So if I do like this, at any moment, either it is here, at any moment. If there is variation in x on positive side, then dz by dt, what we saw, the rate of change on vertical side with the change in unit change in time, that will grow or not, that will also grow. So actually, okay, it is same thing what we calculated earlier. When time is constant, then with unit variation change in x, how much unit variation in vertical side, dz by dx. Now keeping x constant with unit variation in time, how much is the vertical change per unit change in time? So f xt xt f tx xt. Now keeping x constant with the unit variation in the time, how much height is changing? If I know that, then at particular instance, at that moment when, so string can be like this, like this, like this, like this at any moment of the time. So at any moment of the time, when we know the string variation, okay, dz by dt, then that variation would grow with the unit change along x-axis. How much it would grow unit variation along the x-axis? That is f tx xt. Okay, so that would also grow in same fashion. So ftx xt and fxt tx are same. If you are in confusion, then you can consider t as y. So we have x-axis and we have y-axis. Okay, so we have x-axis and we have y-axis. Now, if I am calculating fxy xy, fxy xy, then keeping y constant. So, okay, keeping y constant at any y, we calculate fx. Now, keeping the x constant in this direction. So, I am shift y. So, delta y I shift. Here y is 1, here y is 1. So, if there is a variation in delta y, then how much dz by dx would change? So dz by dx we have already calculated at one y. At another y, dz by dx, so dz by dx already calculated in along x-axis. So at one point I have to calculate dz by dx, where if it comes as a function of y, then I have to substitute as a y1. Like fxy is x square into y. So it will come as 2xy. fxxy, fxxy, fxy is x square into y. Then fxy, xy, fxy is x square y. So fxxy is 2xy. So it is function of y. So what is fxxy when y is y1? What is fxxy when y is y2? Now, for that I have to calculate 2z value and delta z by delta y. If I calculate that, then it becomes fxy xy. So first partial derivative along x-axis, and then whatever derivative came as a function of y, then along y-axis. Now fyx xy. So first I have to calculate, keeping x constant at any x, what is dz by dy? At any x, what is dz by dy? So at this x, I have to calculate z value for this y, and then y I have to shift, then again I have to calculate z value. If I calculate this, then dz by dy is then delta change in z by delta change in y is dz by y. So at particular x in 2y, I calculate dz by dy. At particular another x, at 2y, I calculate dz by dy. So I have received 2 dz by dy at 2x. So difference, I just I need to subtract. And 2 dz by dy2, dz by dy at y2 minus dz by dy at y1 divided by delta x. So we calculated fyx xy. Earlier we calculated fxy. So fxy xy, we have to calculate f dz by dx at y1, dz whatever is there, again here dz by dx at y2, and we get fxy xy. fyx first we have to calculate at any x, what is the at any particular x, for particular y what is z value, same x for another y what is z value. If I differentiate z delta z by delta y, we get dz by dy at that x. At another x we calculate z value. At same x we calculate z value again against 2y value. delta z by delta z by delta y dz by dy at x2. Now we have dz by dy at x1, dz by dy at x2. Then I have to subtract dz by dx at both locations and divide by delta y. So both comes to the same. So same thing we have to apply it in fxt also. So fxt xt and fts tx xt would be comes same. The way it comes the same. Now we talk little bit about the local linearity. So if I have a sphere, okay. So if I have a sphere, then it looks like a sphere. Simple, right? It looks like a sphere. But if I bring the sphere near to my eye, I am seeing it as a flat surface. The way I am sitting on Earth flatter, but Earth is not flat. If someone see Earth from space or from moon, it is a sphere. But if you come along and touch the Earth, then at a particular point it looks flat. Okay. Now there is something called local linearization. Local linearization is a surface. So at any point, how the what is should be the equation of the flat surface. Okay, so that we calculated the equation of the flat surface it comes as fxy. Then it will be fxxy or m1 into x plus m2 into y, where m1 is fxxy, m2 is fyxy. So partial derivative along x-axis and partial derivative along y-axis. So the local linearization surface equation fxy would be fxxyx plus fyxy into y. Same thing we do in single dimension. Y equal to mx. If y equal to mx, then for the surface it will come as z equal to m1x plus m2y. If it passes through point A and B, we are calculating at point A and B, then it will come as m1 x minus a plus m2 y minus b. Okay, so that is the local linearization surface equation. Now, but if this is point AB we are calculating it, if we move little bit around, then it will come as a slight error. Okay, because what we calculated the surface touching, so the gradient, the tangent surface touching the sphere at that point, there it will be accurate. But if you go little bit here and there, then approximation, so whatever the surface equation we have estimated, fxxy or gxy equal to m1 x minus a plus m2 x minus b, then for x equal to a and b, y equal to b, it is perfect. But if you go delta x and delta y here and there, then it will be approximate. So how we can go for exact approximation more? So when we have double differentiation, then we can add double differentiation component also. So that if we move from a comma b point around in the neighbor little bit, then it will be more accurate. So then we have to calculate the double difference, the how much it would change as per the in the second dimension also. So earlier it was m1x plus m2y or m1x minus a plus m2y minus b, or z equal to m1x minus a plus y m2y minus b, or z minus z0 equal to m1x minus x0 plus m2y minus y0, where z0 x0 y0 are the point where it is passing through. Now we have to add the dual differential so that it will be more accurate. So we have to add now fxx. So earlier fx x minus a plus fy y minus b. Now plus fxx x square. So fxx x minus a square by 2 plus fyy y minus b square by 2 plus, now there are two fxy and fyx. So by 2 not required. So fxy x minus a into y minus b. So net equation of the local linearity, the surface would be, or rather I could say graph, would be that gxy or fxy equal to fx x minus a plus fy y minus b plus fx x x minus a whole square plus fyy y minus b whole square plus fxy x minus a into y minus b. So this would be kind of more appropriate local linearity. So that we should ponder about, we should think about.